Find failed queries, reformulations, and abandonment patterns fast with DuckDB. This is the pattern you'll be able to implement by the end, which groups events into sessions and surfaces reformulations, zero-result sequences, and abandonment counts. I'm Professor Pi, teaching search and IR with simple Python. Search logs are full of clues. A single zero result can hint at a missing document. A sequence of changes can reveal how users refine queries until they find something. Success looks like fewer zero results, faster fixes, and targeted ranking improvements. DuckDB gives you fast, local SQL analytics inside Python. It is ideal for exploratory work on tens of thousands to a few million rows, without the overhead of a full data pipeline. At a high level, we will load tiny logs, compute a baseline zero result rate, find which users see the most failures, split interactions into sessions, then mine pairs where a failed query was followed by a successful reformulation. That pattern points to fixes you can automate or prioritize. You will see how a few SQL window functions and simple aggregations produce actionable metrics. Next, we'll initialize a minimal in-memory example to get a reproducible baseline quick. This snippet initializes an in-memory DuckDB database, writes a tiny search log table, and reports the overall zero result rate. The variable con is the DuckDB connection created with DuckDB connect. The statement con.execute creates the logs table with compact columns: U for user, TS for time, Q for query, R for result count, and C for clicks. The call con.executeMany inserts 3 example rows, so we have stable, deterministic data. The query calculates the share of queries with zero results using an average over a case expression. Then the Python print formats the percentage to 2 decimals. The printed zero rate quantifies how frequently queries produce no results, a foundational failure signal. Now, we'll add a few rows to see how failure exposure concentrates by user. This example appends a few more log rows with con.executeMany, and then uses DuckDB to rank users by failure exposure. The new rows add a later query for user U1, an improved query for U2, and a new user U3 with a zero result query. The select statement groups by the user column U and computes each user's zero result share using an average of a case expression. Ordering by ZR descending surfaces the worst user with a tiebreaker on user ID for deterministic selection. The fetch1 call returns the single highest rate user and their percentage. The printed worst user and ZR highlight where to prioritize fixes or guidance. Next, we'll turn timestamps into meaningful sessions, so consecutive queries are grouped sensibly. This code creates a sess view in DuckDB that assigns session IDs by user based on a 3-minute inactivity gap. The select uses lag over a partition by U, ordered by TS, to compare each query's time with its previous one. When the previous timestamp is missing, or the gap exceeds 3 minutes, the case emits a 1. The running sum over the same window turns those markers into a session counter SID. The follow-up query counts distinct user session pairs to verify segmentation. If you increase the gap, more queries merge into fewer sessions. Decreasing it splits sessions more aggressively. The printed sessions value confirms how many navigable sessions the logs contain. Now we'll extract consecutive query pairs inside those sessions to find helpful reformulations. This snippet extracts consecutive query pairs inside the DuckDB sess view to find reformulations that turn zero results into results. The subquery T computes normalized queries NQ using lower, alongside prior values PNQ, PQ, and PR via lag by user and session. The main query keeps pairs where the normalized text changed. The previous result count was 0, and the current result count is positive. Then, groups to count occurrences. Ordering by n highlights the most common successful transition. Normalizing with lower reduces duplicate noise. Adding trim or simple plural handling would further improve signal and can change which pair wins. The printed best pair and count show your clearest win pattern to replicate. Next, we'll collapse sessions to measure outright abandonment, where nothing was found and nothing was clicked. This example computes a simple abandonment baseline from the DuckDB sess view by collapsing each session into outcomes. The common table expression S aggregates clicks and results within each user session via max, which serves as a proxy. If any query had results or a click, the max is positive. The outer select sums sessions, where both MR and MC are 0, dividing by the total number of sessions to get a percentage. This spotlights sessions that likely ended with no useful content and no engagement. The printed abandon rate quantifies how often users leave without finding anything, a high priority signal for ranking and recall improvements. In a real product, this tiny recipe maps directly to monitoring. Use the reformulation pairs to build query rewrites. Use the worst users and abandonment rate to prioritize tests. Combine these metrics with offline relevance checks to close the loop. Recap. It is a lightweight DuckDB workflow that finds 0 result rates, reformulation wins, and session abandonment. Use it when you have search logs and want fast explainable signals before heavy modeling. One caveat is that simple normalization misses spelling and synonym patterns, so results are noisy until you add more text processing. Wrap punch. Next, tune the session gap parameter to see how sensitive your reformulation counts and abandonment rate are to different timeout choices. If short, practical IR helps, subscribe and watch the IR videos.